A class is like a recipe or a blueprint. It tells you what something can be made of and how it can behave, but it is not the thing itself. An object is the actual thing you get when you follow the recipe. Deeper view: in memory, a class defines a type, a collection of fields that is data and methods that is behavior. The type is stored once, often in a method table, and each object holds its own copy of the fields while sharing the method code. Practical example: imagine a dog class written in Java. Public class dog open brace, private string name semicolon, private int age semicolon, public void bark open parenthesis close parenthesis open brace system dot out dot println open quote woof exclamation mark close quote semicolon close brace. Public void set name open parenthesis string name close parenthesis open brace this dot name equals name semicolon close brace. Public string get name open parenthesis close parenthesis open brace return name semicolon close brace. Close brace. When you write dog buddy equals new dog open parenthesis close parenthesis semicolon, buddy is an object, a concrete dog that lives in heap memory with its own name and age. You can create many dog objects such as Buddy, Max, and Bella that all share the same class definition but have independent state. Analogy: think of a dog class as the recipe for a chocolate cake. It lists ingredients, which are the fields, and steps, which are the methods. Each time you bake a cake, you get a tangible object you can eat, but the recipe itself never changes. Why it matters? Separating the idea, the class, from the concrete instance, the object, lets you write reusable, modular code and reason about program structure without being tangled in individual data values. Inside a class, we store two main things: attributes, also called fields, and methods. Attributes are like the pieces of Lego that belong to a toy: color, size, weight. In code, they are variables that hold data, for example, name, age. They can be primitive types such as int or double, or references to other objects. Methods are the actions the toy can do, like bark or run. They are functions that live inside the class and can read or modify the object's attributes. Visibility: access modifiers. Public visible anywhere. Typical use is an API that external code should call. Private visible inside the same class only. Typical use is internal state that must not be touched directly. Protected visible to the same package or subclasses. Typical use is to allow inheritance to reuse behavior. Package private visible to the same package. Typical use is a group of related classes. Why visibility matters? It enforces information hiding. If a field is private, other code cannot corrupt it accidentally. They must use a controlled getter or setter that can validate the data. Practical example: C#. Public class rectangle opens a block. Inside it declares a private double width and a private double height. It defines a public constructor rectangle that takes a double W and a double H, and sets the width property to W and the height property to H. The public property width has a getter that returns width and a setter that assigns width to the supplied value if the value is greater than 0. Otherwise, it throws an argument exception with the message width must be positive. The public property height works similarly for height. Finally, a public method area returns width multiplied by height. Here width and height are hidden. The public properties enforce that they stay positive. The method area uses the hidden fields to compute a value. Takeaway: by carefully choosing visibility, you protect the integrity of the object's state, while exposing only the behavior that makes sense for other parts of the program. Explanation: creating an object is called instantiation. Think of a cookie cutter, the class that you press into dough to make a cookie the object. The constructor is the special method that runs right when the cookie is cut. It sets up the initial state, like giving the cookie its shape and sprinkling chocolate chips. What a constructor does. Memory allocation: the runtime reserves space for the new object's fields. Initialization: the constructor assigns values to those fields, often using parameters supplied by the caller. Invariant enforcement: the constructor can validate arguments and throw exceptions if the object would be created in an illegal state. Overloading constructors. Many languages allow multiple constructors with different parameter lists. This enables constructor chaining. A more specific constructor can delegate to a general one to avoid code duplication. Java code defining a class dog with private string name and private int age. The primary constructor takes a string name and an int age, calls setName with the name and setAge with the age. The convenience constructor takes only a string name and delegates to the primary constructor with age 1. The setName method assigns this name to the provided name if it is not null and not blank, otherwise to the literal unnamed. The setAge method throws an illegal argument exception if the age is negative, otherwise assigns this age to the provided age. When new dog with buddy and 3 runs, memory for a dog object is allocated, then the constructor assigns name buddy and age 3. The object is now ready. Static factories alternative to constructors. Sometimes static methods like dog.of with name and age are preferred because they can return subclasses, cached instances, or perform extra logic. Keypoint: the constructor is the only place where the object's internal state is guaranteed to be fully initialized before any other code can interact with it. Encapsulation is the practice of keeping the inside of a class safe and tidy, like putting a fragile toy inside a padded box. By using access control private or protected attributes, we stop other parts of the program from accidentally changing important data. Instead, we provide public methods getters and setters that check the data before it changes, ensuring data integrity. Why encapsulation matters? Invariant protection guarantees that the object never enters an invalid state. Implementation hiding allows you to change the internal representation without affecting external code. Modularity, each class becomes a self-contained unit with a clear contract. Public class bank account, private double balance, public bank account double initial. If initial less than 0, throw new illegal argument exception negative balance. This balance equals initial. Public double get balance returns balance. Public void deposit double amount. If amount less than or equal to 0, throw new illegal argument exception deposit must be positive. Balance plus equals amount. Public void withdraw double amount. If amount less than or equal to 0, throw new illegal argument exception withdrawal must be positive. If amount greater than balance, throw new illegal state exception insufficient funds. Balance minus equals amount. The balance field cannot be set directly from outside. Every change must go through deposit or withdraw, where we enforce rules: no negative deposits, no overdraft. This keeps the account's data consistent. Immutability as a stronger form of encapsulation. Public final class point. Private final double xy public point double x double y. This x equals x. This y equals y. Public double x returns x. Public double y returns y. Immutable objects are inherently thread safe and simplify reasoning about program state. Bottom line, encapsulation is the guardrail that prevents accidental misuse and makes future maintenance far easier. Every object has an identity, its unique address in memory, and a value, the data it holds. Imagine 2 identical twins. They look the same values, but are different people, different identities. In programming, triple equals or double equals in some languages often checks identity, whether 2 variables point to the exact same object. To compare values, we use an equality method like equals. Identity comparison. In Java, obj1 equals obj2 returns true only if both references point to the same heap object. In Python, does the same thing. Value comparison. Default equals method in many languages falls back to identity unless overridden. Overriding allows you to define what equal means for your type. Overriding equals Java example. Public class point. Private final integer x and y. Public constructor takes x and y and assigns them to this .x, and this .y. Override equals method taking an object O. If this equals O, then return true. Identity shortcut. If O is not an instance of point, then return false. Type check. Cast O to point P. Return this .x equals P.x, and this .y equals P.y. Value comparison. Override hash code method, returning 31 times x plus y. Now 2 distinct point objects with the same coordinates are considered equal. Mathematical perspective. For numeric types, value equality often follows mathematical equivalence. Example, 2 rational numbers 2/4 and 1/2 are value equal though their internal representation differs. A custom rational class would need to reduce fractions in equals. When you use identity versus value. Identity is needed when you care about object identity, for example caching, graphs where each node must be unique. Value is used for domain objects where logical equivalence matters, for example string, big decimal. Practical tip, Always override hash code together with equals when objects are used as keys in hash-based collections. Hash map hash set. When an object is created, the computer allocates memory for it, like giving a new house a plot of land. When the program no longer needs the object, the memory can be freed. Some languages have garbage collection, an automatic cleanup crew that looks for houses objects that no one lives in and demolishes them, returning the land memory to the system. In languages without automatic garbage collection, you may need a destructor or finalize to manually release resources, like closing a file or freeing a big image from memory. Stack versus heap. Primitive local variables often live on the stack, fast allocation and deallocation. Objects are usually on the heap, managed by the runtime. Object header. The runtime stores metadata, type pointer, garbage collection flags, lock word, alongside the fields. Garbage collection algorithms. Mark and sweep. Traverse reachable objects, mark them, then sweep free unmarked ones. Used in simple Java virtual machines and Net Classic garbage collector. Generational. Separate young and old generations. Collect the young generation frequently because most objects die quickly. Used in modern Java virtual machines and Net Core. Reference counting. Each object tracks how many references point to it. When the count reaches 0, it is freed. Used in CPython with an additional cycle collector. Concurrent or parallel. Garbage collector runs in parallel with application threads to reduce pause times. Examples include G1 garbage collector, Z garbage collector, and Net server garbage collector. Destructors or finalizers. In C++, you write tilde class name parentheses to release native resources such as files, sockets, GPU buffers. In Java, the finalize method exists but is deprecated because its timing is non-deterministic. In C#, you implement idisposable and use using blocks to guarantee deterministic cleanup. Example of deterministic cleanup in C#. Using a file stream opening data.txt with file mode open, a using block opens the file stream. Inside the block you work with the stream. After the block closes, the file stream dispose method is called automatically, releasing the file handle. Memory leaks. Even with garbage collection, leaks can happen when you keep references unintentionally, for example static collections or event listeners. Monitoring tools such as profilers and heap dumps help detect such leaks. Takeaway: understanding how memory is allocated when it is reclaimed, and how to release non-memory resources is essential for writing robust, performant software. Reusing code saves effort. Inheritance lets a new class called child borrow everything from an existing class called parent and add its own twists, like a golden retriever class inheriting from the general dog class but adding a special fetch method. Interfaces are contracts that say any class that signs this must provide these methods without saying how. It's like a toy factory promising every toy will have a play button. Composition means building a class from other classes, like a car class that contains an engine object and a wheel object. This is similar to building a robot from separate Lego pieces. Heading inheritance. Bullet 1, single inheritance in Java and C# means one direct parent. Bullet 2, multiple inheritance in C++ and Python means a class can have several parents and can lead to the diamond problem solved by virtual inheritance or method resolution order, MRO. Bullet 3 is a relationship means a subclass should be substitutable for its superclass, which is the Liskov substitution principle. Example in Java. A public class named dog defines a public method bark that prints woof. Another public class named golden retriever extends dog and defines a public method fetch that prints fetching. Golden retriever inherits bark automatically. Heading interfaces or protocols. Bullet 1, define what methods must exist, not how they are implemented. Bullet 2, allow multiple contracts to be satisfied, enabling flexible design. Example in Java. A public interface named playable declares a method play. A public class named toy car implements playable and overrides the play method to print vroom. Heading composition over inheritance. Bullet 1, favor has a relationships, meaning a class contains instances of other classes. Bullet 2, reduces coupling and avoids fragile base class problems. Example in C++. A class engine with a public method start. A class wheel with a public method rotate. A class car contains an engine object named engine and a vector of wheel objects named wheels. Car has a public method drive that calls engine start and then rotates each wheel. Here car reuses engine and wheel without inheriting from them. Heading, choosing the right strategy. Table, for goal shared behavior and polymorphic substitution, the best fit is inheritance if is a holds. For goal shared contract across unrelated hierarchies, the best fit is interface or protocol. For goal reuse of functionality without type relationship, the best fit is composition. Design tip, start with composition. Switch to inheritance only when a clear is a relationship exists and you need polymorphic dispatch. Mathematical analogy. A vector space can inherit from set, which is a relationship, but also compose a field object to define its scalar multiplication. This combination illustrates how both inheritance and composition can coexist in sophisticated models. Explanation, to turn real-world or math ideas into code, we model them with classes. Example, a bank account class with attributes balance and owner and methods deposit amount and withdraw amount. For math, consider a vector 2D class with x and y attributes. It can have a method length that returns square root of x squared plus y squared, the Pythagorean theorem. By writing these classes, we capture the important traits and behaviors of the real or mathematical objects, making them easy to work with in a program. Steps for effective modeling. Identify nouns, they often become classes, such as dog, account, vector. Identify verbs, they become methods, for example, deposit, withdraw, add, normalize. Determine attributes, the state each object holds, such as balance, owner, x, y. Define invariance, rules that must always hold. For example, balance greater than or equal to 0, vector components are numbers. Choose relationships, inheritance, such as specialized accounts, composition, where an account has a customer object, or association, where a vector interacts with a matrix. Python code, defining a customer class with name and ID number attributes, and a bank account class that composes a customer, validates the initial balance, provides a balance property, and defines deposit and withdraw methods with validation. The bank account class encapsulates balance logic and composes a customer. Java code, defining a vector 2D class with immutable x and y fields, a length method that returns the hypotenuse using the Pythagorean theorem, add and scale methods that return new vectors, and overridden equals and hash code methods. The length method directly implements the Pythagorean theorem, showing how mathematical formulas become class behavior. Tips for high-quality models. Keep it minimal, only include attributes and methods needed for the problem domain. Favor immutability for value objects. For example, vector 2D makes reasoning easier. Document invariance in comments or with assertions. Write unit tests that verify real-world scenarios, for example, depositing a negative amount throws. By translating the essential characteristics of real or abstract entities into well-structured classes, you create a bridge between the problem domain and executable code, enabling clear, maintainable, and testable software.